Welcome everyone to this extremely interesting webinar today, organized as part of the doctoral school series of webinars of the Faculty of Chemistry and Chemical Technology of the University of Ljubljana in collaboration with the European Research Infrastructure for Heritage Science. And it's my absolute pleasure to be able to introduce Dr. Josep Grau-Bove, who's Associate Professor at the Bartlett School of Environment, Energy and Resources at University College London. I've had the pleasure of knowing and working with Josep for a long period of time, and I know that he finished his chemical engineering studies in Barcelona, in Catalonia. But lately, he's been extremely active as Professor of Heritage Science, studying technologies for preventive conservation, including the development of tools for the analysis of environmental data, with which he's been incredibly successful. I'm absolutely sure that he's going to tell us a little bit more about that today. He studied transport phenomena in heritage materials and environments involving computational fluid dynamics, which our chemical engineers will know very well, particularly to study pollutants, rain, and particulate matter, which is the topic of today's lecture. He's also very interested in citizen heritage science and crowdsourcing of data. And unfortunately, or perhaps yes, Josep will talk a little bit about that today as well. But if not, then that's a really interesting topic for a future webinar. Among his excellent recent successes is the introduction of the Masters in Science in Data Science for Cultural Heritage, which has been an incredibly successful course at UCL, specifically aimed at those interested in data science within the broader cultural heritage environment. Without further ado, Josep, you have a very, very big task on your hands today. We have a very varied audience of chemistry students, perhaps a few conservators, and collection managers as well. So I'm absolutely delighted about your lecture, and over to you. Thank you very much.
Thank you very much, Mattia. Thanks for the introduction. Also, thank you, Marco, for the introduction, and thank you very much, Irina, for the invitation. It's a great pleasure to be here, and also to be able to talk about a topic that it's so dear to me, because I started researching the topic of particulate matter in my PhD dissertation, which feels a long time ago now, even it's not so far in time, but I've done so many things afterwards that now talking about it, it's unavoidable to feel I'm remembering good times in some ways, even though the latest paper published from this research is from 2019 or so. There's a little bit of citizen science as well in this presentation, not only CFD, so thanks, Mattia, for remembering this as well. Particulate matter is absolutely everywhere. Everywhere where there's human activity, there's particulate matter in the air. It's unavoidable, it's always there. And that's what makes it an interesting agent of deterioration in heritage, which is that we cannot eliminate it. We can only learn how to live with it in an efficient way, let's say. Unfortunately for us, we live in a very sticky universe. Wherever there's a surface, particles will stick with it. At the sizes we are dealing with, the van der Waals forces are the forces that dominate relationships between matter. And as long as a particle is close to a surface, it will stick to it. Even the surfaces that are most valuable, that have more people looking at them, more people taking care of them, even the most well-known surfaces in the world will have particles in them. If you go to Google Arts, which I have, they pioneered this technique of being able to photograph pictures with ultra resolution, so you can zoom in almost to the level of a microscope. You can very easily look for dust, and you will see a lot of it. this image, if you pay attention. I hope it renders well on your screens. Otherwise, while I'll talk, feel free to go to Google Arts and Culture and look for any painting that you like and try to find dust in it. I promise you will find it, especially if it's shiny and if the painting has a rough texture. You can imagine that people such as myself with a fascination for this topic have spent some time browsing these paintings looking for dust. And what can we see here? Well, there's a combination of things. There are some fibers, there are some smaller round particles that we can see without further magnification. There are also some darker stains that perhaps are made of even smaller particles that we cannot see individually, we only see their aggregate effect. There are all sorts of things here that could merit further investigation. I'll show you another example. This is the eye of this merchant by Hans Holbein. And in the middle of the eye, there's a white fiber. I don't know if it will be visible in your screens. It's quite clearly visible in mine. I would bet that this white fiber comes from the clothing of some visitor. It is probably even synthetic, is what we would call nowadays a microplastic. So we have now a material which represents the time that this painting has spent in a museum in the 21st century. We have like some evidence of the human activities around it, on it. Is this particle damaging to the painting in any way? Is it aesthetically, does it aesthetically affect our experience? Probably not. Not the single particle anyway. Should it be cleaned? Maybe cleaning it would cause more problems than having it there. But these are difficult questions to answer. And I will try in this presentation to give sketches of answers to some of them, even though I should warn you, I'm much more interested in the things we don't know for sure than the ones we know. So in my presentations, I tend to raise many questions and not answer a lot of them. I want to show you just one other example of dust on a painting. This dust is a lot coarser. These are big particles, and this is in this painting by Monet, which is in the National Gallery. I like this example because it illustrates the fundamental contradiction that we have with dust. It's a material that sometimes should be clean and sometimes shouldn't be clean. This is a case where it very much shouldn't be clean. This is sand from the beach where the painting was painted, and it represents physically the first occasions where painters started painting al fresco. It's also a moment in history where painters opposed academic perfectionism. So having some nature physically attached to their painters was beginning to be something to be proud of and not something to correct. So cleaning this dirt would be a grave mistake. And that's what makes dust so problematic. It's not only that sometimes the same amount of dust can be perceived more negatively than others, is that in some occasions, dust can even be perceived positively. So it's an agent of deterioration where its presence ranges from the problem that should be avoided to the added value to a surface. And when you make plans to mitigate it in a museum, you need to be aware of these apparent contradictions. So it's difficult to manage in that sense. So that said, after this preface, I'll give you, let's say, the structure of this presentation. I will start with a definition of what particulate matter is, then some thoughts on how it affects the value of heritage, and then how can museums mitigate it. I will present some monitoring techniques and also the CFD models that I developed in my PhD, and additionally, some ideas on how citizen science can help. Let's begin. The best way to classify particulate matter is by looking at a logarithmic scale of size and seeing where different types of particles fall into that scale. When I say particulate matter, I mean anything from very fine particles that come from combustion, and that would be the sizes towards the left, so fractions of a micron, to the particles that we have in our surfaces at home, which are some hundreds of microns or even above. And when they are all together, to our human eyes, they look very similar, but their composition and their behavior, it's extraordinarily different, to the point that sometimes I think it's quite silly calling everything particulate matter, because we are talking about things that are so different and have so different effects on surfaces. It's not like a chemical compound, which always will look the same. You know, if you have a piece of particulate matter, that doesn't tell you anything about how it is chemically. So to be more specific, towards the left, with the fractions of a micron, we have very fine particles generally coming from combustion of fossil fuels. The most common one is what's called diesel particulate matter, and they are the ones which are most chemically active. Then 10 times bigger than this, we have viruses, coronaviruses, including the one which is fashionable nowadays, are in this category. At a few microns, we would have mold spores. These are the ones on this size that are perhaps more interesting to cultural heritage. And at the hundreds of microns, we would have household dust, also fibers from clothing, and also the particles that nowadays we call microplastics, even though they are not as micro as other things, and they are a small but quite interesting fraction of the large particles. This classification that I'm showing, I think it can look misleading. If we put things into scale, we gain some perspective. So that's actually the difference of size there is between these particles. Now you can imagine that this complicates measurements very much. The first consequence that it has is that it makes these particles very difficult to count. If we are interested in seeing how many of them there are, we'll be only counting the small but numerous, which is diesel particulate matter. If we start counting how much mass of them, if we weigh them, we will only be counting the ones that are large, but there are few. So depending on whether you're interested in number or you're interested in mass, you're going to be measuring different things, which makes risk assessment in a museum quite difficult. To make things more complicated, if we are interested in area, the thing that you are measuring is something in between. And I'm going to show some experimental data that demonstrates this later. So it's difficult to know, it's difficult to have a good quantification of the problem, really. Another consequence of this wide divergence of scales is that you can never photograph them together. In this image here, I am showing a particle of coarse dust. It's probably a mineral particle, and I think you'll be able to see its spherical shape quite easily. There are also some that are not so spherical, are more difficult to see. It is embedded on a piece of paper. That's a very smooth, white piece of paper, but it looks like this on this level of magnification. We can see the individual fibers. You can see that the particle is of more or less the size of the pores of this piece of paper. We can also see that if this particle here makes around 100 microns, the particles that are a fraction of a micron are of the size of a pixel. If you want to see them, you need a microscope powerful enough to be able to frame only a few of these pixels on the screen, and therefore in this image, you will never see the big particle. So it's impossible to count both types of particles at once. If you decide to count them with a microscope, you need to choose whether you want to count big particles or small particles. So we have a separation of scales. We are looking really at very different microscopic worlds when we talk about big particles or small particles. However, it is of some benefit to consider their problems as an aggregate. So in this presentation, I will have to be clarifying slide by slide whether I'm talking about big particles or small particles, because I have a little bit of everything. So the first question that we need to ask ourselves is, what are the impacts of these particles depositing on valuable surfaces? How do they reduce the value of heritage? There are several kinds of effects. There's a potential aesthetic effect because they make the surfaces look dirty. And even though this one, as I have said, it's very complicated, it's perhaps the one that we understand the best so far. It's also been hypothesized that they are a breeding ground for pests and insects or perhaps mold. And even though that's a hypothesis that it's quite solid, I believe, we don't have a lot of experimental evidence or epidemiological evidence showing this. we don't know that in the dustiest buildings we have the most mold, for example. This has not been shown experimentally that I know of. Then there's also the potential that by being on surfaces, we are going to induce more frequent cleaning and therefore put the surfaces at more risk of physical abrasion. Or it could also be that just by being there, the particles make cleaning even more difficult, so that cleaning has to be more intense. That's also a reasonable hypothesis, and there's some anecdotal evidence here and there, but no systematic studies. And also, it could be that they interact chemically with surfaces. And about this, we have some evidence. I have some evidence in this presentation. We're going to discuss it a little bit. So let's start problem by problem. I'm going to concentrate mostly on the aesthetic effect and the chemical degradation, because the other ones I know little about. Yes, and they're, let's say, I think we can consider them all open questions in some ways. So let's start with the aesthetic effect. This result, I've been using it in presentations for a long time, and it's been cited many times by people monitoring particulate matter indoors, because it's a very good experiment that demonstrates at which point we should start worrying about area coverage by particulate matter. The experimenters asked several participants whether they were able to see that the surface was dirty. And they changed the amount of little black dots on this surface by increasing the percentage of coverage by carbon. It's black dots on a white surface, so it's a very idealized system. But what you can see is that on around 4% area coverage, most of the observers correctly identify a surface as dirty. And that has been an influential result because it has led to the definition of acceptable thresholds of deposition. So some institutions can use this type of data to say, okay, I don't want to reach 5% area coverage by particles, so that's going to be my monthly limit, for example. Or I am going to clean when I know that I reach this. By the way, that's a good slide to ask you. You don't have to answer because there's a lot of people in here, but I would be interested to see what you think. So maybe you can comment on the Q&A afterwards. Whether you have read the text on the screen. There is some text in gray. It's been here since the beginning. It's been increasing in grayness by 1% every slide, actually. And I wanted to see whether it would become visible at 5%. Then the one that you're looking at now is around 8%, I think, or 9%, and we can count the slides later. So if you don't see it, if you saw it earlier, it means you are in the average of this result. I have a few slides that make it a little bit darker, so ensure that everyone sees it. I think this is as dark as it gets. So if you have seen it like 4 slides before, you are within the average that this study predicted. Now, it would be excellent if that was the only factor. If we knew that 5% area coverage always meant that we would have a negative reaction from visitors to museums. Unfortunately, reality is a lot more complex, and not only because some paintings will have some very valuable anecdotal dust like this Monet I was showing, it's a much more general phenomenon. Have a look at these reviews in TripAdvisor. One is a review of a building visited from the outside, the cathedral in Canterbury. The other one is a review of a church visited from inside. And in both of them, the reviewer comments that the building was too clean. In one of them, it says, it was too clean and fresh to make an impression of antiquity. So there is an expectation among some visitors that there will be dust that will contribute positively to their experience. This may look quite surprising, but in fact, it has been detected in other patterns of degradation. We don't have evidence directly for dust indoors, which is the main area of interest of this presentation, but we have evidence from other similar processes. For example, there's the blackening of external surfaces in buildings, the blackening of facades, and this is a process that involves particulate matter of combustion, originated in combustion, but also involves other chemical processes. But never mind, it results in the surface becoming darkened. Some years ago, Peter Brimbelkom and Carlotta Grossi produced this super interesting study where they asked different participants what's the level of unacceptability that they connected to several patterns of deterioration of a building. And they found there was a wide difference of opinions, and it depended very much on the type of pattern. So for example, if a pattern obscured the architectural detail, visitors tended to consider it more negatively. But if it simply made the building a little bit darker, it could even be considered to make it look more appealing or historically correct, if you will. I am sure that if we repeated this study in indoor spaces looking at dust, we would see similar results. And that the public of a building like the one on the right, which is a prison in Dublin, would be a lot more accepting of that dust deposition than the public of the building on the right, which is the Guggenheim Museum in New York. I'm sure we would get the same level of dust, would get different evaluations in one context or the other. And that's, I would say, perhaps another open question. We have, again, anecdotal evidence, and some publications have mentioned the potential for this, but we don't know exactly what conditions would lead to what kind of evaluation. That's as much as I can say about aesthetic effects. Now I'm going to move on to the chemical effects, and that's, I have a single slide on this, but it's a slide with a lot of information in it. That's an experiment that, in fact, I did in collaboration with the Heritage Science Laboratory in Ljubljana some years ago. What we did was placing samples of paper in several locations in London, and we let dust deposit on it of all sizes, coarse and small. In some locations, there was a lot of dust from lots of fine particles coming from vehicles. In some locations, there was more dust coming from visitor activity, let's say. So it was indoors and outdoors. At the same time, there was a study that did exactly the same, or a very similar approach made in the Czech Republic, actually. And they were published in the same year. And their results are quite similar, which I'm very glad to see. And I think there haven't been further studies on the topic, so maybe we close this question. The fact that there are two studies in the same year with similar results, it's quite nice. What it shows, maybe some of you are familiar with this notation. So you can see on the vertical axis, it says dP in both cases. dP is the degree of polymerization. The chemists or the paper chemists in the room will know that this is an indicator of the average length of the chains of cellulose, and that if it's low, it's bad, if it's high, it's good. So here we are evaluating how the presence of particles reduces this value. In both cases, the particles cause a reduction of around 400 points of dP. There are a couple of differences between the two studies. The main difference is that in our study, we explored which of the multiple components of the particles was contributing more to this degradation. And what we found is that the concentration of iron within the particles correlated very well with the loss of degree of polymerization, or it was the element that correlated the best. So the main conclusion that we can take from this is, firstly, that it's not the amount of particles what dictates the chemical deterioration of the cellulose. It is the composition of those particles. You could have very few particles of very aggressive composition doing more harm than lots of particles which don't interact with it. That's the first lesson. The second lesson is that we only obtain a pronounced reduction in degree of polymerization in the surfaces where we had extreme amounts of deposition. The surfaces that had invisible amounts of deposition that couldn't be seen with the naked eye, the degradation was almost negligible. And the lesson we can take from this, it's simply that if you clean before dust is visible, or before dust is irritatingly visible, let's say, you are also protecting your surfaces from chemical degradation. Of course, here I'm talking only about a single material. I'm also talking about an aggregate measurement of the effects of lots of types of particles simultaneously. There are still many unknowns, for example, the specific role that microplastics could have, thinking that they have complex additives that may migrate to surfaces and so on. So there are lots of unknowns, but I think that was a good first step, and at least it promises that if you clean, you're probably also fine, chemically speaking. Okay, I am going to move on to the final section of my presentation, concentrating more on monitoring and management strategies. I am going to use a case study, which is this fabulous building. It's called Apsley House. It's managed by English Heritage in the UK. It's in London. It was the house of the Duke of Wellington. It used to be known as London number 1 because it was the first prominent house you found in London when you came from using the road from Bath. It is, unfortunately, very poorly placed on the busiest roundabout in London. There's a lot of traffic in front of it, and that makes it an interesting case study because it suffers a lot from pollution coming from the cars, mostly diesel particulate matter. It's also visited quite frequently. Lots of school groups go there. It's very popular. It has a fantastic collection of paintings that attracts visitors from all over the world. So it has also a problem of coarse dust deposition. It's an interesting combination of fine particles coming from outside and coarse particles coming from within the building. It's a very common combination, but that's one case where both processes are equally important at the same time. You will find mostly in certain buildings, one matters more than the other. Here it's a case where you get a good amount of both types of particles. So what I did there was monitoring dust deposition in several locations for a year, which was an interesting opportunity of experimenting with different ways of monitoring dust. There are basically two main approaches. One is that you place a sensor a monitoring device that captures particles in the air, airborne concentrations. Option B is that you look at the dust that has already deposited on surfaces, that you place some small surface that you know it was clean at the beginning, and you let dust accumulate for some time. These are the main two approaches. When I am asked which one is the best, I always, in Heritage, I always advise for option B. There are several reasons for this. Firstly, it is very cheap. You can do it in several ways, but to start with, you only need a flat surface, which could be a piece of glass or a piece of reflecting plastic, and a microscope. Then it has the advantage that what you are measuring, it's exactly what you are worried about. You are worried about how many particles reach your surfaces. And with this kind of monitoring approach, you actually measure how many particles reach your surfaces. If you measure airborne concentration, you have the advantage that you can get data every second if you want, but you have the permanent disadvantage that you only know how many particles you have in the air, not in the surfaces. It's very good to estimate risks to health, but it's not so good to estimate risks to heritage. And we cannot translate easily from particles in the air to particles in the surfaces. I will show you later why that's not as easy as it seems. So I monitored this in many locations, not only in this building, in others as well. First thing I found out is that if I plotted the particles by the percentage of area that they were covering, the most problematic ones were not the big ones or the small ones, but the ones in between. Even in Apsley House, even outside of Apsley House, next to the road, where we have some of the highest concentrations of diesel particulate matter, not only in London, but in Europe, I would say, we have a very high concentration. Even there, these particles are so small that they don't contribute much to covering surfaces. They're very numerous, but they're very small. So they don't make the surfaces as dirty as other particles, which is quite interesting. I mean, having a surface, 1% of a surface covered with black soot is a lot. And still is not as much as what you could get with a smaller amount of bigger particles. That's one of the things. I mean, this dependence on size and number is one of the things that makes this data difficult to plot, but also difficult to prioritize what's the biggest risk for a given environment. Another thing that I did was comparing these measurements of deposition of particles of different sizes against simulations using computational fluid dynamics. So I developed a model that produced colorful simulations like this. What this image is showing is the internal spaces of this building, of Apsley House, colored according to some of the parameters that the model predicts. In the image above, what we are seeing is the indoor-outdoor ratio. So it's the concentration of particles of a certain size. So you need to do separate simulations for separate sizes. So it's the concentration of particles of a certain size divided by the concentration of particles outside. That helps you make your simulations independent of each specific day, because the concentration outside changes very much. It's different in the morning than in the afternoon. It's different in a weekday than in a weekend. There's no cars on Christmas, for example. But whatever is the situation, I know that I'm going to have 60% of what I have outside inside. And that's why I like this kind of plot. The image below shows the air velocity. The air velocity is how the simulation starts. So basically you need to calculate how the air is going to move across the whole building and how it moves as a consequence of mechanical ventilation, of natural ventilation, of heating, creating areas of warm air that will raise up, and so on. And once you have your profile of air velocity, then you can drop your particles on it and see where the air takes them. That's basically the principle behind this kind of simulation. If someone wants to ask more specific questions, I'll try to reply if I remember how I did it, because equations are forgotten easily once you look away from them. So this model is really powerful. It gives you a lot of information. It probably, as with many models do, it gives you more information than what you need or you can even process with our little human brains. But what I wanted to do more than anything else is to compare this model not against measurements of concentration, because that's relatively easy to do. And as I was saying before, it's not what we are mostly concerned about. What I wanted to do is compare this model against measurements of particles on the surfaces. When I set out to do this, I didn't know it was such a silly idea. It's extremely complex for many reasons. And I'll show you a complicated plot, but if you bear with me, I think it illustrates some of the complexities of this kind of monitoring and of this kind of simulation. So let's look at this plot with some attention. In the x-axis, horizontally, you will see the names of several rooms. You don't need to know what they mean. There are several rooms on this building. On the y-axis, we have a deposition velocity. That's a parameter used in the business of particulate matter to study how fast particles deposit, or what's the capacity of particles, what's the capacity of an environment to attract particles to the wall, let's say. This is all for particles of a certain size, which, if I remember correctly, it's also half a micron, but it doesn't matter. It's for a single size right now. The black boxes, the whisker plots, show the experimental measurements of deposition velocity. The first thing to note is that the error is gigantic. The error bars, and you have to consider that this scale is also logarithmic. These error bars are very, very, very big. And that's not because I'm very bad at taking measurements. As I was saying, you only need a glass slide and a microscope in order to count how many particles you have on them. So it's not rocket science, and it's very easy to do very precisely. The problem is that these measurements depend this deposition depends on so many things. It depends on how many visitors are in the space. It depends on whether the ventilation system works or not. It depends on the heating. It depends on the opening times, whether there were school groups, whether there were cars, on the wind outside. It depends on so many things. So when you measure, I think I did measurements every week, perhaps, or every 2 weeks over 12 months. When you average those, you get a lot of diversity of results. However, is there any signal among this noise? Notice that there's a pronounced pattern between different rooms. So the average changes a little bit. There are some rooms with less deposition than others. So that's good and potentially useful for validation. And all the interest here lays in trying to see which simulation predicts these differences between rooms. If you look at the lines, the red lines, blue lines, and green lines, they indicate different runs of the model in different scenarios. In one scenario, the bottom one, we assume that the only entrance of particles is the main door of the building. In another scenario, we assume that the only entrance of the particles is the small gaps of the windows. So because the windows don't close perfectly, they're a little bit old, a little bit leaky, so air flows through small gaps. And then in the final scenario, we assume that particles enter through all these gaps, but on top of that, there's a ventilation system moving the air around. So what this plot shows is that you cannot really explain the differences between rooms if you don't consider the effect of ventilation. That's the kind of way you need to, that's how you need to interpret this kind of results. So you run scenarios and you have to think which of the scenarios that you have run is the one that contains the factors that explain the variability of the data. It's very hard to use simulations otherwise. There's a very high risk of overfitting. With CFD, if you know how to tune it, you could get any output with any input. So your scenarios need to be rooted in the operation regions of the building. Okay, I want to zoom in a room to tell you something else about the physics of these kind of particles. We'll talk about very fine particles now, so the particles that come from the street. And we're going to pay attention to that room at the bottom indicated by the red arrow. That's a room that displays a quite homogeneous concentration of particles. So the particles get in this room through the main entrance of the building, which is not far, and through gaps in the windows. And they mix quite well. So these particles are everywhere. If you breathe in the one corner of this room or in the other, you're going to swallow the same amount of particles. However, if we look at the deposition rate of these particles, so how many particles reach the surfaces, that's what this simulation is indicating. And you can see that the units are in particles per square meter per second. So that's a flux of particles. You can imagine like a rain of particles reaching a surface. So if you measure or simulate this, you're going to see that the result is very different depending on whether the ventilation is on or off. What does it mean? It means that if we are just measuring the concentration of particles in the air, we are not going to be able to estimate how many will reach the surfaces, because this depends on how we use the room. The amount of particle that reaches the surface, it's a function of two things. How many of those are there, obviously, because there are no particles, known deposits, but also how much deposition is promoted by air movement. So you need to know both how many particles you have and how much your air moves. And that's a little bit tricky sometimes. That it's a case for small particles. It is not the case for very large particles, because very large particles just fall to the floor like a dead weight. They are less influenced by air motion. So last slide on the model before I wrap up. It's just on a slide, an image I'm fond of showing, because it shows an alternative way of displaying this kind of result. In the previous slide, I was using this metric of number of particles per square meter per unit time. Some values were 100, some values were 1,000. I don't have any idea of what these values mean. They are too abstract for me, even though I produce them myself. But if you tell me in this room you have 100 particles per square meter per second, I don't know if I should be worried. I don't know if it's fine. Maybe I'm in my flat, maybe I'm in a sandstorm, I don't know. So I worked hard to try to make visualizations that could lead to action, that could inform decision making. Of course, the more you elaborate a visualization, the further you get from the outputs of the model, the more assumptions you need. So there's a balance to be obtained. In this case, this plot is showing for all the possible sizes of particles that are in this room, all of them in aggregate, they will deposit on surfaces, they will cover a certain area. At some point, we're going to reach an amount of area that we consider unacceptable. We're going to reach a percentage of area coverage that we consider unacceptable. I'm taking 5% because it's similar to that plot, but each institution could choose anything. So what this image shows, it's the amount of time before we reach the unacceptable area coverage. And that can be linked immediately to cleaning routines, for example. And you can see, all right, I am cleaning this every month, so I'm all right. I'm avoiding my limit of 5% area coverage, for example. Final block of the presentation, only a couple of minutes left. Smartphones are everywhere, and many people have had the idea that since visitors carry smartphones everywhere, it may be a good idea to try to see whether we could get any useful information out of them. This has many benefits. It also, if it works, could produce lots of interesting data, but it also engages visitors in preventive conservation and conservation science and raises the profile of our discipline. So in many ways, it's a no-brainer. We did some tests with the smartphones indoors, and we put signs next to objects in museums, requesting visitors to take a picture. Our objective was to use these color charts that you see in the image to calibrate the smartphones, calibrate the submissions, and fundamentally use the smartphones as a colorimeter. We published a paper on this a couple of years ago. This work has been repeated by another group recently who has improved our correlations massively, actually. This is an example of the kind of correlations that we obtain. We did them for different color combinations. That's the example from white to black. And what you can see here is the correspondence between the color measured with a smartphone on the left-hand side and the color measured with a very good colorimeter on the x-axis. And there's a correlation. It's remarkably good in some areas. We did this for every color, and we then produced this image. This image indicates for every color of the color chart, one value, it's the absolute difference between, so if you take a picture of this color with a smartphone, the value at the top in each cell will indicate how far you are from the true color, and the value at the bottom, it's the error, it's the width of the distribution of values that you would get. What matters now in this slide is that if you compare all the colors, you will see that the ones that have smaller values are the ones in the grayscale from white to black. In fact, if you look at the error that we would get, it's usually around 4. It gets bigger if you get darker, but in the pale grays, it's 3, 4, and so on, with remarkably small standard deviations, I would say. Now, you remember what this value looks like, this 4.1, 3.4. This is similar to the value I was showing you initially. This is similar to the value I was showing you initially, which is could be considered a threshold on which area coverage is unacceptable of black particles on a white surface. So we are almost there. Even with this relatively simple correlation that, as I say, has been improved upon, we would already be able to detect deposition with pictures taken by visitors just before it is visible to the visitors themselves. This is what the data indicates, even if it looks surprising, of course, under the right lighting conditions and so on. And I'm sure the experimental complications of doing this in a museum would make it quite difficult in practice. You know, there's angle, there's lighting conditions, there are other variables that we should control for. But it's theoretically possible, and I believe worth trying out. That's everything. Thank you very much. I look forward to your Q&A.
Thank you so much, Josep. I think you've made us as excited about dust as possible, which shows how what an excellent communicator you are. I enjoyed your presentation immensely. I think my mother would probably disagree with your aesthetic criteria because she made me clean my room every week, regardless of the area coverage. So I think your model could be improved a little bit. But I think what you've shown us is how important it is to combine knowledge of extremely different areas of expertise, from chemical engineering to analytical chemistry to environmental chemistry and conservation in your case as well, to address what is seemingly a very simple question, but requires an extremely complex response in order for that response to be useful. Thank you very much indeed for this.